So here in this problem type of combinatorial argument, we are going to learn a beautiful technique of solving a lot of sequence and series problems that we can solve using combinatorial arguments. So let us start this without a lot of wasting time. Let us go for the first question. Suppose we want to just add up n choose 0, n choose 1, n choose 2 till n choose n. Now all of us know that this equals 2 to the power n, right? But suppose we are asked to prove that. Suppose we are asked to prove that. How we will prove? The basic proof, the algebraic proof that we all are aware of. Just we'll write the binomial expansion of 1 plus x whole to the power n, and then we will put x equals to 1 and prove it, right? But what is, this is the method 1. This is the method 1. Now let us go for the method 2 of this proof. That is using combinatorics. We are going to solve this summation problem. How can we visualize this sum? Let us set a scenario. Let us set a scenario. So in all those problems, when we are going to solve a sequence and series sum using combinatorics, what we do is basically set up a scenario. Set up a scenario where we will get this sum. Where we will get this sum. Just follow the steps. You will understand that how to set up the scenario. Like here, if you just take a general term and choose k, just let us consider a general term. That's choosing of k things out of n things, right? And we are just adding this up. Can we say that if we are having n students and we want to make group of students from n students, how many ways are there to make this group? So the first question obviously that comes to in our mind, that group of how many students, that is not mentioned in the question. Group of how many students, that is not mentioned in the question. You can create group of 1 student, 2 student, 0 student and n students. So when we create group of 1 student, what we take? N choose 0. When we create group of 1 student, we do just n choose 1, n choose 2, right? So on, n choose n. So group of students from n students is basically this sum. This is one way of making group of students from n students. Now what we can think, we have n students. We have n students. Say set of students. Let me name the students as S1, S2, so on, Sn. And we want to make a group of students. So this group, this is the group. Let me write it as G. And this group of n students, this all the students set, let me write it as A. A denotes the set of all the n students, right? And G is the group that we are making. In how many ways we can make this group? See, every student S1 has two options. Either he will go into the group or he will not go into the group. So every student has two options. Similarly, S2 has, he will go into the group or he will not go into the group. He also has two options. So on, we will multiply them 2. And there are n students, so this will give us 2 to the power n. In this way, when we equate the sum, because both are same thing, we're just thinking them in different ways, we'll get this as 2 to the power n. So this is the power of using combinatorial argument to simplify things, simplify a lot of sequence series problems, especially those kind of problems what we will encounter. When we will think of this approach, things to note. Whenever you will find this symbol n choose k, okay, or some factorial symbol, say r factorial. Whenever we will find this, whenever we will find n choose k or some factorial term in summation type problems, we can think of this approach. Now, one thing to note is that if plus and minus signs alternates, then using this approach is usually not helpful. Why? Like this sum was something like this: n choose 0 plus, sorry, minus n choose 1 plus n choose 2 minus n choose 3. So the easier approach of solving this was using binomial theorem, right? So whenever plus and minus signs alternate, this approach is a little bit on the tougher side. Okay, but sometimes like we can isolate the positive, we can isolate the positive terms and the negative terms, and then we can do something. This is also, there is also a possibility. So these are two things that we need to keep in our mind whenever we are solving sequence and series problem using combinatorial argument. So this was the introduction of how we use combinatorial argument in sequence and series, and let us solve another question. We'll solve question number 4. So this, there is a given summation that we need to solve. Fantastic. So this is okay, there are some limits of this. What is happening? Okay, let me write it soon. The system has probably hanged. Just wait a minute. Yeah, so all right, it's all right now. So let us solve the sum. Again, we can see that things to note point that whenever there is some n choose k sign, we'll think of this approach. So let us just write few terms of this question to understand that how we are going to solve it. 10 choose 0, 20 choose m plus 10 choose 1, 20 choose m minus 1, 10 choose 2, 20 choose m minus 2, so on. So here we can observe that what we can observe, see this sum 0 plus m is m, this sum 1 plus m minus 1 is m, this sum 2 plus m minus 2 is m. Like always we are giving you the observations, the approach, the problem types that we need to keep in our mind when we are going to solve a problem. Otherwise, all if we think for a long time, we can solve any problem definitely. But if we know some things, if we know some observations, it becomes easier for us to solve the problem. So they all are adding up to m. So what we can say is that, and here we can see that this sum is 30. We are selecting m things out of 30 things, right? M things out of 30 things. So let me just write it in a more precise way. Say there are 10 boys and 20 girls, and we want to select M. There are students, they all are students. There are 10 boy students and 20 girl students, and we want to select M students out of them. In how many ways we can select? Okay. So, like, we'll say that 30 choose M, 30 choose M. In another way, we can think of it that casework. Let number of boys that we are choosing be 0. Number of boys be 0. This is the case 1. Number of boys in the group that we are selecting. This is the group of M students. Be 0. Number of boys be 0. So number of girls are obviously going to be M. How many ways we can choose? 10 choose 0, 20 choose M, right? 10 choose 0, 20 choose. Let us take the second case. When number of boys 1. Number of girls will be M minus 1 because total number of students is what? M in the group. This we can select in 10 choose 1, 20 choose M minus 1. So this cases when we are adding them up, we'll get this series, right? 10 choose 0, 20 choose M plus 10 choose 1, 20 choose M minus 1 plus 10 choose 2, 20 choose M minus 2, so on, right? We'll get this sum. That's the required sum. So this same question of choosing M students out of 10 boys and 20 girls is 30. And when we do this using casework, we get this sum and they are equal, right? So this sum S is nothing else but 30 choose M. And using basic, what is the demand of the question? S is maximum, find the value of M. To maximize this using basic ideas of binomial theorem, we know that this will be maximum when M equals to 15. Okay. For that, you can refer to, these are the very basic things in normal classrooms, any classrooms, J11 classrooms, these are discussed, how to maximize this. So this is how we will apply combinatorial argument. Let us go for the next question. See the third question. That's again a beautiful question. The third question. So let us try to solve this question. Here also we can see the note point is working. 12 choose 2, 12 1 into 2. So how we are going to solve this question? Like, first of all, let me give you the algebraic approach for this question. It's a very basic classroom question that we solve. All of these are classroom questions, right? But here we are showing you the approach to solve this, and you won't find them in such an organized way. X plus 1 whole to the power n. Let me make it whole to the power 12. This will be 12 choose 0, x to the power 0 plus 12 choose 1, x to the power 1, 12 choose 2, x square. right? This is what we are getting here. Now, see, we want to simply just maximize this sum. How we're going to maximize this sum? How will maximize this sum? No, what am I saying? We just want this sum, right? From this, what am I saying? Sorry, we just that previous question of maximization is still running in my head. So we want this x to the power 1 here. This is the first term, like not the first term, but quite anonymous to the first term. If we differentiate x square, what we'll get? 2x. If we again differentiate it, what we'll get? 2 into 1, some x to the power 0. Again, for the third term, when we double differentiate it, we'll get 3 into 2 x, right? So can we see that this is what we have been asked for? 1 into 2, 1 into 2, into 12 choose 2, 2 into 3, into 12 choose 3, and there you will say that no sir, extra x is there. What we will do with the x? Just put x equals to 1. Okay, so we can easily observe that double differentiating this and putting x equals to 1, we'll get this sequence. So this side should also be double differentiated, and then we will put x equals to 1. So let us double differentiate x plus 1 whole to the power 12. What we will get? This is the required sum that we are going to find out. First, 12 into x plus 1 whole to the power 11. First differentiation. Then again we are differentiating it. 12 into 11 x plus 1 whole to the power 10. Now we will put x equals to 1. 12 into 11 into 2 to the power 10. So this is the required sum using binomial theorem. Now we are going to solve the same problem using combinatorics, and you will find that approach very interesting. Whenever these terms are there, we need to think of making groups, kind of groups. Okay. Method 2, combinatorial argument. So let us solve it using combinatorial argument. Let us just take a general term out of the series. I need the series in front of my eyes so that I can solve it in a better way. Fantastic, fantastic. Just we'll just solve it. Very easy. See, let us take this term. 12 choose 2. One thing that we need to observe. Total number of things that we are choosing from a 12, right? Total number of things that we are choosing from a 12. Always 12. So there is some set A. We'll say a set of students S1, S2, S12. And we are choosing students out of them. But just 1 into 2, like some extra options. If we say that we are choosing a group of 12 students, then this is not going to be a fair thing. Say we want to make a group of students G, group of students G, in which there will be a captain, okay, there will be a captain, and there will be a vice captain. There will be a vice captain, and rest are the other members, right? So what we can do, we can go for casework. Casework will give us this. Casework will give us this. And directly when we are solving, we'll get the direct sum, required sum. Okay. So let us go for casework. Just learn the approach, not the question. The same question is not going to be asked. The approach is useful. So let us think of the first case. Since there is captain and vice captain, the minimum number of students that we need is 2, right? Minimum number is 2. When number of students in the group G is 2, number of ways of choosing the captain 2. Okay. Now one person is chosen as the captain. The remaining number of choices are for vice captain is 1. And we are selecting 2 students, right? Total number of students, very lengthy lecture, 2. So 12 choose 2. Another thing will be multiplied. Again, for the second case, when total number of students in the group are 3. Okay, number of ways of choosing the captain is 3. Vice captain is 2. And choosing 3 students out of 12 students, 12 choose 3. So individually, when we'll add the case works, different case works, we'll get this sum, we'll get this sum. Now, without casework, without casework, there are 12 students and we need to create a group in which there is a captain, there's a vice captain, and there's the remaining number of students. For the captain, choosing captain out of 12 students, how many options do we have? 12, right? And for vice captain, how many options do we have? 11, right? Now there are remaining students. Remaining students. How many students that we are left with? 10 students, right? They can go there, cannot go there. So any students can go into the group or cannot go into the group, cannot go into the group, right? So this has 2 to the power 10 ways. Just we discussed this in the very first example. In this example, we discussed this here. Here we discuss this concept. Okay. So they can go there, cannot go there. This is what is the required sum. Simple argument. When you are solving this with binomial theorem, you need to first write the sum, differentiate it 2 times, and then get the answer. And here, just think of a case. Think of a case if you have a good thinking ability, definitely. And then just find out using PNC how many fractions of second, how many fractions of minute will it consume. Okay, not going to consume a great deal of time. Yes, obviously. Now let us solve the last question. There are 2 more questions. This question is same. This question is same as the question that we solved just now. So this you can take as a homework. We're going to solve this question, question number 1. So this is a very interesting question because we said things to note that there should be some n choose k sign, but here is no n choose k sign. Yes, obviously. We said that whenever you will see n choose k sign in summation, you think of this approach. We didn't say that if you are not seeing n choose k sign in sequence in series type problem, you cannot think of. This is a kind of a proof that you all are going to love this proof because we all have studied this proof using the formula of a cube minus b cube. But today we are going to learn a totally different version of this formula, proof of this formula. So definitely you guys are going to love this proof. So this is your homework. This is your homework. Let me take it outside the screen and focus totally on this. This is your homework. You can take a screenshot of this. Range of k, range of k, 2 to 13. Range of k is 2 to 13. from k equals to 2 to k equals to 13. Okay, this is the homework. You can take this. Let us focus here. Let us focus here. How we are going to approach this question? I'm not going to show you the algebraic proof for this. Never, 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 never. This is going. I'll show you the combinatorial proof for this. I'm going to love this proof. So just let us write this in a different way. This is what 1 into 1 plus 2 into 2 plus 3 into 3, 3 into 3 plus n into n. Can you just assume it that we are having this case 1 into 1, or let me take more general case 3 into 3, 3 into 3. Say we are having some x, y, and we are given some that x and y have some three choices. Okay, x and y have some three choices. How many choices does the combination of x and y have? Means when both x and y are chosen, how many different choices? Like, what can I say? Like x and y, x comma y belongs to the set 1 2 3. Okay, belongs to the set 1 2 3. Fantastic. X and y can be any number among this 1 2 3. How many different pairs of x comma y exist? We'll say ordered pairs 3 into 3. How many different ordered pair of x and y exist? 3 into 3, right? This is what we are getting here, 3 into 3. So in this way we are going to sum up the entire scenario. But here one thing we can see every time as we see here, x and y belongs to the set 1 comma 2 in this way, and here 1 2 3. So every time there is a upper bound, you can say upper bound. Let us set that upper bound as some z, that z is greater than both x comma y. Z is greater than both x comma y. Precisely, we can write it as z is greater than maximum of x comma y. Okay, z is greater than maximum of x comma y. So when z is 3, sorry, z is 4, x comma y belongs to 1 2 3. Okay, x comma y belongs to 1 2 3. I am asking you, when z is 4, how many ordered pairs of x comma y you can make? You will say 3 into 3, right? In this way we are proceeding. So the range of z, range of values of z is what? Starting from, since the last value x and y is n, the range of values of n should have a maximum bound of n plus 1. Maximum should be n plus 1. And you will say that z starts from 2. Fantastic, fantastic. But I will say, let us consider 1. Okay, 1. 2 is also included. We'll say x comma y comma z belongs to this set such that z is always greater than any of max of x comma y. And when we go through casework, we will say z equals to 1. Z equals to 1. Okay. Number of choices for the ordered pair x comma y. Number of choices. Find number of ordered pair z x y. Number of ordered pair z x y or x y z, whatever you write doesn't matter, right? We're not writing coordinate of a certain point. So when z equals to 1, we are going for casework. Casework, as I said, casework will give you this sum. Casework will give you this sum, and we'll use p and c. We'll get the value of this sum, right? So when z is 1, case 1, x comma y has no values, no values, no values, 0. When z is 2, x comma y can take only one values, 1 into 1. When z is 3, they have 2 into 2 possibilities, 2 square. So on. When z is n plus 1, x comma y can take values n into n into n different values x comma y can take. And when we'll add this sequence, we'll get some 0 square plus 1 square, 2 square, so on, n square. This is what we're getting using casework, right? Now, what is the scenario that we have, or what is the situation that we have created? That xyz belongs to this set such that z is greater than max of x comma y. We need to find the number of ordered pairs of z x y, okay, or x y z. So now we will solve this using PNC, pure PNC. X comma x y z belongs to 1 to 3 n plus 1, z greater than max of x plus y. This has three cases. See, z greater than x greater than y, or z greater than y greater than x, or z greater than x equals to y, right? This statement has three cases. So in how many ways you can select ordered paired x, y, z for the first case, z greater than x greater than y? Just simply you will say n plus 1 choose 3, right? Here also you will say n plus 1 choose 3, and here you will say n plus 1 choose 2. We're correct? Yes. So x is equal to y, right? So this is what is the required sum. You add them up, what you will get? N plus 1 into n minus 1 by 6 factorial into 2. Hey, not 6 factorial, 6. 3 factorial plus n plus 1 into n by 2 factorial. Okay, add them up, you will get n into n plus 1 into 2n plus 1 by 6. That is the sum of first square of first n natural number. So this is the useful tool, combinatorial argument, and we have shown you the power of this. You can take another homework for this combinatorial argument. Find the sum of 1 cube plus 2 cube plus 3 cube, so on, n cube, using combinatorial argument. This will be, I guess, question number 6. So there are 2 questions you can take in your home as a task. Thank you.